Welcome to our advanced power electronics and control courses in NPTEL. We shall continue with your matrix converter and thereafter we shall see that different kind of power quality issues briefly. So, let us discuss where we have left. We are discussing with the indirect matrix converter. We have discussed different topologies. These are the recapitulations of the previous class. There are different kind of topology has been discussed and the switching count is also been discussed, and now come to this point actually how actually it has been controlled. So, generally inverter part is essentially a a 2 level inverter or the 3 level inverter depending on the actual rating of the switches, but you can consider a Sparse matrix here with the reduced switches. So, we will consider actually UA is actually instead of sine cos. So, actually that is the most positive phase at the 0 instant, and accordingly UB will be 120 degree phase shifted and UC will be 240 degree phase shifted. So, at the beginning at the instant you can see that this is basically this dotted line actually this dotted line is essentially is the UA, and you will be switched in such a manner that maximum DC maximum DC will be coming to this fictitious DC post voltage. So, what will happen and you can see that, and at that time C is the most negative phase, and that is what will happen you will get a ripple that. So, you will actually conduct the phase A, upper leg of the phase A of this switches and lower leg of the phase C, so that you get the voltage UACR. Similarly, you can see that this is basically after this interval, after 30 degree interval, after 60 degree interval at this point, B will be the most positive phase, C continued to be the most negative phase, then you will be switching B and C, positive part of the B switches and negative part of the C switches. So, you will get BCR. Accordingly, all the switching sequence will become AC, BC, like that you are continue to get. So, UA, UB, UC are the 3 phase input voltages at the amplitude of having these are the amplitude and the angular frequency omega, and omega t equal to 0. You can see that actually it is a balanced 3 phase system. So, actually summation of this 3 instantaneous voltage will give you 0, hence actually UA equal to 1 and UB equal to minus 0.5 and UC equal to plus 0.5, and so you are here basically this is 0.5 minus for B and 0.5 minus for C, and A here will be a 1. So, essentially if you subtract minus 0.5 and 1, so you are going to get essentially the maximum voltage 1.5 time of the line voltages. Then C continued to be actually down, and thus your voltage will increase and it will change over at the point of actually 60 degree from actually 0 crossing, but here 0 crossing start at an instant of pi by 2. So, these are the sequence how you will switch it on. You can see that. So, this is the upper leg and this is the lower leg. So, at 0 to 60 degree upper leg UA will be switched on and there will be a changeover at 30 degree to B to C, and thus actually PN voltage, that is this the pole to neutral voltage will be AB and AC. Similarly, pi by 6 to actually pi by 3 you will have this sequence UAB and UN equal to UC, and this will be the voltage. So, these are the sequential curve with the 30 degree interval of time. So, it will be changeover every 60 degree. So, UA will be there for the period of 60 degree Similarly, UC will be there for the period of 60 degree. So, automatically this switching pattern will take place. So, and thus you get a maximum desealing voltage, fictitious desealing voltage in that manner. Now, how you will generate? Let us consider that you have a, we have discussed already that you are changing the frequency 25 hertz to 50 hertz, or you are actually 50 hertz to 100 hertz. So, this is your input space vectors and where 110 where we discuss about POO in are similarly to be POO. So, this is basically PPO. Similarly, you have a two level space vector, and this will be mapped to the actually space vector which is rotating maybe the 2 omega or 3 omega. If it is rotating at a speed omega, so what we require to do, we have to actually split these vectors in between, and we are sure that basically if we want to generate some voltage here in this sector, same voltage will be actually generating here at the input at the output of this indirect matrix converter. So, it will be the combination of the 1 to 7, where 1 is actually 100, 2 is 110, or in terms of the Benhu's actually book, actually it is POO, it is PPO. So, this, and you will have this V1 and V2, and thus you got a Vref here. So, let us see how you will generate this. Now, this is the switching logic, and you have to calculate the same way you have calculated the actually the time for the action of voltage vector V1. So, that is for AA1, that is minus 1 by root 3 U2, this is basically the unit vector, into Tp is the processing time cos omega t into UC, and this time essentially will be equal to T1. Basically, why? You know this voltage applied here is AC, and it is for the duration for 60 degree for actually alpha plus pi by 6. So, for this reason this is T1. Similarly, for T2 we will have to have a sine component, and this should be minus 1 by under root 3 this term Tp sine of alpha UC equal to T2. So, you subtract T1 and T2 and you get the T0. First, of course, you start with the voltage vector T11 110, thereafter actually it will be 100, thereafter you will have, of course, you have to apply the null vector, that is T0, that will be basically 111, thereafter again you will apply 111, thereafter again we will apply 110, then 100, then 110, then again 111, again this sequence will be repeated. So, here if you see that this is basically the USE, so this will be the sequence to be followed for these 3 switches, and thus you can generate these voltages in this configuration. Now, this is the desealing voltage you will get, the ripple DC you will get, since there is no since there is no output voltage, no capacitor to filter it out or smooth out, you will get a ripple voltage every 60 degree interval. Ultimately, you can see that this interval, so it will be around 60 degree. And similarly, this will be the phase output voltages, which will be converted for actually for This is basically the output simulation results, practical results can be shown later. That is for the 30 ohm with the 50 hertz applications. Now, here this is the output line voltages and this is the output phase current, and which you will find to be sinusoidal, and ultimately it gives a better results than the sine triangle PWM, and THD is quite low for this actually filters. Now, this is the hardware setup. We are making the practical hardwares on it, and we shall show this results later. Now, let us come to the one main challenge of this actually inverter topologies or AC to AC direct conversion. Problem is that your voltage, output voltage is reduced than your input voltage. So, this is one of the biggest disadvantage to direct AC to AC conversion, and to mitigate this problem, for this reason we require to have some kind of boosting stage to boost up the voltage, and this can be done and this can be incorporated into the directly AC to AC conversion. We have already discussed about the Z source inverter, and here in the Z source inverter we have discussed in our class few classes ago. So, it is introduced by the FZ Peng, and this is once actually you short it, these two capacitor comes into the series, ultimately voltage becomes basically Vc1 plus Vc2 and you get a higher boosting effect. Can we have a same kind of concept incorporated in direct AC to AC conversion? So, that is the challenge we can see. So, we know that actually it consists of the 2 inductor and the 2 capacitor, and it generally performs 2 mode of operation. One is the shoot through mode, that means when you actually short the switches. Please refer to my lectures of the Z source inverter. And in case of the shoot through mode, diode remains off and inductor gets charged by the capacitor, and the input voltage and the one leg of the inverter get shorted, and thus boosting operation is achieved. Now, in case of the non shoot through stage, the diode remains on and inductor discharges and the output voltage get boosted up, and in this condition inverter part acts as a current source. Here boosting factor is calculated by considering the average voltage across the inductor over a cycle 0, and boosting factor of actually this Z source inverter is 1 by 1 minus 2 ds. So, you can maximum actually give a 50% duty cycle. So, otherwise there will be a instability. So, 2 types of quasi Z source inverters has been given below. This is one of the case of the quasi Z source inverter. We had, please refer to our discussions of the Z source inverter. It is just the recapitulations. So, this is a continuous mode of actually the Z source inverter and quasi Z source inverter, and this is a discontinuous mode of quasi Z source inverter where inductor current is quite low, and we prefer to actually have a discontinuous mode of the quasi Z source inverter. Now, this is the extension of the quasi Z source inverter, that is called extended boost Z source inverter. After quasi Z source inverter, researchers were actually focused on increasing the boosting factor further. So, how can we actually boost this actually ratio, that is actually 1 by 1 minus 2 d. So, it is limited to actually the some value. So, this value is basically 0.5, and can we actually get it actually at a reduced value. For this some passive impedance network were added, and you can see that instead of actually 2 inductor you have a 3 inductors, and finally we can have another boosting effect. and finally in 2010 a new DC to DC converters was proposed known as the extended jet source inverter. This extended jet source inverter consists of the 3 inductor and the 3 capacitor and the 3 diode, and during short through condition diode D1 D2 remains off, but the diode D3 is forward biased and it is on, and thus it pumps a continuous energy. The shoot through stage, all the 3 inductor gets charged by the capacitors, and during no shoot through stage the diode D1 D2 remains on and D1 remains off, and the inductor gets discharged to the boost out the output voltage. And so, overall boosting stage is been achieved is 1 by 1 minus D into 1 minus 2D. So, huge boosting can be achieved with the help of this actually enhanced boosting capacity. So, let us incorporate that Z source concept into the parts matrix. So, in spite of many advantage, that is what I was saying, this matrix converter also has some disadvantages. Voltage gain of the matrix converter is limited to 0.866. Output voltage may be affected by the gate voltage changes when there is a decrease in the gate voltage, and it affects the output voltage as the matrix converter does not perform the boosting action. Though by changing the modulation index, output voltage can be controlled, but it is up to some range, and voltage gain of the matrix converter, direct matrix converter is limited to 0.866. So, that is the limitations of it. By adopting over modulation technique, but it can increase the voltage gain, like third harmonic injection and all those technique can be applied here, but it degrades the quality of the output voltage and the input current. So, THD will be the casualty there, and also you do not get much of the boosting. By integration of the AC boost chopper with the matrix converter, variable output voltage can only possible, but not variable frequency operation. So, it not allow the variable frequency operation, it can allow only actually fixed voltage operation. The gain is increased by adding some passive elements block in cascade with the conventional basic impedance network. In this lecture, one of the Z source SMC topology has been discussed for the lack of time. So, this is actually a topology. It is actually, this part is already we have discussed, this is a DC part, this is a converter part and this is inverter part. In between you have added this actually the boosting network, and here you can see that with this not only you can actually control the frequency, but also you can control the, of course you can actually buck it by changing the modulation index, and this part of the circuit can help you also to boost it. Thus, it is a basically a idealized solid state transformer. So, it is fine, it will be highly used in future with the penetration of the silicon carbide based device. We should use this device, this topology and the variant topology as a actually solid state transformer. It will be compact, it will be a very useful thing, and it will be less bulky, and you have a lot of other advantages. Let us see how does it work. Here is a quasi Z source network is incorporated between the rectifier and the inverter as shown in the figure. The quasi Z source network consists of the 2 inductor L1 L2 and the 2 capacitors C1 C2. In between there will be a shoot through stage. Mainly the inductor plays a vital role in boosting the voltage. It also consists of a bidirectional switch and the bidirectional power flow. So, sometime we may not actually, or you can use for regenerative braking also. It is not that power flow is this way, it can be also in this way. So, here we require sometime a bidirectional switch. So, this is the configuration. So, you have a input stage intact as working to generate the DC-link voltage, and you will apply the shoot through into your actually inversion stage, and thus what will happen, you will be boosting a voltage Vc1 and a Vc2 above your VDC, and thus what will happen, Vc1 and Vc2 will come and it will add up this DC link voltage, and you will get the extra DC link voltage to be converted into the extra AC side line voltages. This is basically the shoot through stage, and this is the non shoot through stage. We will consider that one CSI is connected. So, it performs the two mode of operation, shoot through mode and the non shoot through mode, to maintain the symmetrical condition only Vc1 equal to Vc2 and VL1 will be VL2. In shoot through mode, the bidirectional switch remains off and any one leg of the inverter is shorted. Here inductor gets charged by the rectifier output voltage and corresponding the capacitor voltage, and if you apply KVL, minus VDC minus Vc1 plus VL2 equal to 0, or minus VDC minus Vc plus VL1 equal to 0. In not shoot through mode, this bidirectional switch remains on and the inductor discharges to the capacitor to boost up the voltage, and by applying KVM, what essentially we will get, VL1 equal to Vc1 and VL2 equal to Vc2, and thus what happen, so VD, you can equate these two equations, Vd plus Vc1 into Ts minus Vc1 T minus Ts equal to 0, and thus Vc1 equal to Vdc Ts by T minus Ts, where Ts is the shoot through stage and T is the total time and D is the shoot through ratio. In that way you can boost up the Vc1. So, again applying K, so you can find it out that basically the overall gain is just in case of a simple boost, simple Z source network, that is 1 by 1 minus ds, where ds stands for the shoot through ratio, that is shoot through by the total time period. Now, let us switch over the topic. So, it requires little conclusion. Actually, we have discussed the direct AC to AC conversion. We have started with the bulky SLICO converters that are gradually moved to a slick devices like matrix converter, and we have seen the problem of the matrix converter. Then from this matrix converter we have come down to the actually direct matrix converter to indirect matrix converter, and from the indirect matrix converter we have actually derived different topologies and also actually made the challenge of the actually boosting up the voltage. Gradually, actually these days are not far behind when we will see that instead of this actually all this copper transformer, these are replaced by the silicon carbide based transformer, and you will see that very slick and bulky, instead of this bulky heavy transformer, we will see that a very compact slick transformer, and it is quite useful where weight is a major concern like aircraft, etc. The term electric, now let us switch over to the another important topic, that is basically the power quality. Power quality is actually issue is a popped up due to the advancement of this power electronics, because as long as voltage and current was sinusoidal with a linear load, there is no problem, and there was a problem with the power factor, and that can be minimized with the reverse kind of load by a var compensator. Now, due to the advent of the power electronics and its rampant usage like adjustable speed drive and other applications, power what we get, it is been virtually polluted. Now, I as a consumer, I want actually a clean power from the utility, but unfortunately due to penetration of the power electronics, power quality get degraded. So, our now discussions will be focused on the power quality. So, let us define power quality. What is it? The term electric power quality is generally used to assess and to maintain the good quality power at the level of generation, transmission, distributions and utilizations of AC electrical power. Modern distribution system, the power quality is vulgarized due to the large amount of the power electronics devices, but unfortunately we wanted to have actually the solution through the power electronics only. The programmable logic drives, adjustable speed drive, lightning, flashover, equipment failure, faults, voltage, distortion and notches. These are basically spoils or decreases the power quality. Power quality problem is an occurrence manifested in non-standard voltage and current and frequency. If there is a sudden swell and sag of voltage and current and the frequency deviation, that results in failure of the misoperation of the main equipment. So, it is a major challenge nowadays. You can see that different kind of waveforms, all of a sudden notches has come. This is basically a transient phenomena. If notches continue in a cycles, then we have to consider the spikes. Now, all of a sudden voltage has sagged half of the voltage almost. So, this is basically the voltage sag. So, power quality problem may be classified on the basis of the event such as transient occurrence is all of a sudden, thereafter it is okay, or in a steady state. The transient time power quality problem includes the phenomena occurring in the transient natures or impulsive and oscillatory nature, such as voltage dip, voltage swell means actually voltage will go off, short duration voltage variations, power frequency variations and the voltage fluctuations. So, this is the voltage flicker. Now, steady state, the types of the power quality problem include the long durations voltage variations, waveform distortion, unbalanced voltages, notches, DC offset, flickers, poor power factor, unbalanced load current, load harmonics currents and excess neutral current. So, you will get all, and this is basically the voltage flickers, all of a sudden it will flicker, and we can see that with this 50 hertz there will be a low frequency is being superimposed, and due to that it may actually cause lot of damage into the power system. It is very difficult to mitigate this subharmonic, and this is actually the typical case of 3-phase direct bridge rectifier fitting an RL load, and you can see that voltage is far from sinusoid and you get a distorted current. This is a current harmonic. Now, this is the voltage swell all of a sudden time, and this is the unbalanced where one of the phase is basically having a more current than two of the other phases. The classification may be on the basis of the current, voltage and the frequency or the load and supply system. Voltage quality problem, that is voltage distortion, flickers, we have shown it, notches, noise, sag, soil, unbalance, under voltage, over voltage. These are the categories of the power quality. And current quality problem, the reactive power components of current, harmonics, unbalanced current and excessive neutral current. These are power quality problem related to current. Now, frequency related problem, that is the power quality problem, frequency variation above or below the desired base value, you have a shifting, and the power quality problem due to the nature of the load, that is for the, if it is a nonlinear load, this problem arises. Load current consisting of the harmonics and the reactive component of the current, unbalanced current, neutral current and DC offset and so on. And power quality problem due to the supply of the system, voltage and frequency related issues such as notches, voltage distortion, unbalance, sags, swell, flickers, noise, all those things we have discussed. Now, thank you for your attention. We shall continue to our power quality in our next class. Thank you.